This is part 2 of Module 14, where we continue our discussion on transformers. So what have we learned about ideal transformers so far? So if this is our ideal transformer, you have your primary voltage E1, your secondary voltage E2, your primary current I1, and your secondary current I2. We learned that E1 over E2 is equal to N1 over N2, and I1 over I2 is equal to N2 over N1, where N1 and N2 are the number of turns of the primary coil and the secondary coil, respectively. We also learned that from the perspective of the source, this circuit can be replaced by an equivalent impedance, where the equivalent impedance is N1 over N2 squared multiplied by ZL. We call this ZL referred to the primary side. So Z equivalent is ZL referred to the primary side. Lastly, we learned that P1 plus JQ1 is equal to P2 plus JQ2. The power and the reactive power delivered by the source to the primary is the power and reactive power that will be delivered by the secondary to the load. In other words, whatever power it receives, it will pass on. The transformer itself does not consume any power or reactive power. Let's take this example. This is not actually a transformer problem, okay? But we're going to use the results of this example to illustrate something later on in this module. The circuit shown represents a situation where a load is far from its source. Z of F represents the lumped impedance of the feeder wires that connect the source to the load. So this is your source, this is your load. You have a situation where the two are far apart, maybe kilometers apart or tens of kilometers apart. In such a case, you can no longer neglect the impedance of the wires, we call them the feeder, that connects the source to the load. So the impedance is represented by Z of F. Assume the load L draws 10 kilowatts at 0.9 power factor lag at a voltage of 220 volts RMS. Determine the RMS value of the source voltage and the power and reactive power supplied by the source. So we have a voltage here of 220 volts. You have a feeder. There's going to be a voltage drop across the feeder. So expect the source voltage to be higher than the load voltage because there has to be a drop in the feeder. Then we're also asked to determine the power and reactive power that is going to be supplied by the source. Okay, the first solution, I'm going to show you two solutions to this problem. The first solution is a phasor-based approach. Okay. First of all, let me complete the information I need to know about my load. So this is my load triangle. PL is equal to 10,000 watts. This angle is the arc cosine of 0.9. Okay. What is the value of Q of L? So again, the nice thing about the power triangle is you only need to know two quantities and you can compute for all other quantities using geometry. Q of L is P of L tangent of arc cosine of 0.9. And I'm going to get Q of L is 48.43.2 vars. Okay, let's designate V of L to be our reference phasor. There are no phase angles specified anywhere here, so let's just designate V of L to be a reference, meaning to say it has a phase angle equal to 0. So V of L will be 220 at an angle 0 degrees volts. Okay, from the complex power formula, okay, the load complex power is equal to PL plus JQL. So that is equal to 10,000 plus J 4843.2. But this is also equal to V sub L multiplied by, V sub L multiplied by the conjugate of I sub S. Okay. So, I can compute for IS conjugate. That is just 10,000 plus J 4843.2 divided by V sub L, which is 220 at an angle 0 degrees. And by just pressing these quantities in my calculator, I'm going to get 50.51 at an angle of minus 25.84 degrees amperes. And I sub S will be 50.51 at an angle 25.84 degrees amperes. Okay, how can I compute for V sub S? I can compute for V sub S using KVL. So from KVL, V sub S is equal to I sub S J sub F plus V sub L. Okay. So this is equal to 50.51 at an angle 25.84 degrees multiplied by J sub F is given as 0.24 plus J 0.32, and V sub L is our reference phasor. This is 220 at an angle 0 degrees. Again, keying this into my calculator, I'm going to get 238.1 at an angle 2.23 degrees volts. So I already know the answer to the first unknown. The RMS value of the phasor V sub S is 238.1. So this is the answer to my first unknown. Okay, so what is the power and reactive power delivered by the source? Again, from complex power, the complex power delivered by the source is equal to the voltage, the source, multiplied by the conjugate of the current through the source. That is equal to 238.1 at an angle 2.23 degrees multiplied by 50.51 at an angle minus 25.84 degrees. That's I sub S conjugate. And keying this into your calculator, you'll get 10,612.2 plus J 5659.5. S is in volt amperes. But we know that complex power, this is actually P sub S, and this is actually Q sub S. So again, these are my answers. Okay, so P sub S 10612.2, Qs of S 5659.5, and Vs of S 238.1. Okay, let's do an alternative solution. Let's use power balancing. Okay. The power triangle, again, let's draw the power triangle of the load. Okay, this is P's of L equal to 10,000. Q's of L, I already computed that to be 4843.2. So this is watts, this is vars. This angle is arc cosine of 0.9. What I want to compute is the apparent power S of L. How do you get S of L? Well, one way is square root of PL squared plus QL squared. We already know QL squared. But maybe the simpler way is S of L is equal to P of L divided by the power factor of your load, which is 10,000 over 0.9. I'm going to get 11,111.1 volt amperes. But S of L is equal to V of L times I of S. No? We're not talking about vectors here. We're talking about RMS values. Okay? So I can compute now my current, the RMS value of my current. This is S of L over V of L. So this is divided by 220. And I'm going to get 50.51 amperes. Notice that this is consistent with the magnitude of I of S, which we computed earlier. Okay. So the next problem is, we haven't solved any unknown yet, no? We want to determine the value of V of S and the power and reactive power that the source supplies. We can get the power and reactive power at this point. No? The power delivered by the source is equal to the power lost in the feeder plus the power delivered to the load. No? This is law of conservation of power. Whatever power being delivered by the source, part of it is lost here. The remainder of it will be delivered to the load. No? So P of S is equal to P of F plus P of L. But P of F is IS squared times R of F, where R of F is 0.24. So I have 50.51 squared times 0.24 plus 10,000. I'm going to get 10,612.2 watts. And I can do the same thing for Qs of S. No? The reactive power delivered by the source will be the reactive power lost in the feeder plus the reactive power that is actually delivered to the load. So this is IS squared times X of F, the reactance of the feeder, plus Qs of L. This is 50.51 squared times 0.32 plus 4843.2. And I'm going to get 5659.5 vars. So I've actually already computed P of S and Qs of S. So what is remaining is I need to know what the source voltage is. I can do that because I can compute for the apparent power delivered by the source. S of S, again, this is not a phasor, this is a scalar quantity, is V of S times I of S, which is P of S squared plus Q of S squared. I already know P of S and Q of S. So I can compute for S of S, that is 12027.0 volt amperes. So to get V of S, I just divide apparent power by my current. So that's 12027.0 divided by 50.51, and I'm going to get the value which we earlier computed using the first method, which is 238.1 volts. Notice that in this approach, there was no complex math involved. We dealt with scalar quantities and not complex numbers. So this is our answer consistent with the first method. In example 5, we said the source is very far from the load and that a long feeder line connected the source to the load and that the impedance of the feeder line could no longer be considered negligible. Here's what we're going to do. At the source side, we're going to connect a transformer that will step up the voltage. And at the load side, we're going to use the same transformer to step down the voltage to the value it was originally intended to be. Okay. We will assume that the transformers are ideal. Okay. The transformers were designed for a voltage at the low voltage side to be 230 volts and a high voltage side voltage to be 7967 volts. The problem is the same as with example 5. Determine the RMS value of the source voltage and the power and reactive power supplied by the source. For this particular example, we're going to use power balancing. So from example 5, we already computed value of I of L, and its RMS value is 50.51 amperes. Note that N1 over N2 for the transformer is equal to 230 over 7967. We can compute for the RMS value of I of F, the feeder current, by using the turns ratio. I of F is equal to N1 over N2 multiplied by I of L. So that will give us 230 over 7967 times 50.51 or 1.46 amperes. At this point, we can already compute for the power and reactive power delivered by the source. If you take a look at the system, the only places where power can actually be consumed are in the resistive component of the feeder impedance and in the load. Remember, our transformer cannot consume any power or reactive power. So the power delivered by the source will be the power that is dissipated in the feeder plus the power delivered to the load. But the power dissipated in the feeder is equal to the feeder current multiplied by the resistive component of the feeder impedance. So to this we add the power delivered to the load. So this is 1.46 squared times 0.24 plus the power delivered to the load is 10,000 watts or 10 kilowatts. And this will give me 10,000.5 watts. And we can argue the same for the reactive power. Q of F is the reactive power that is absorbed by the feeder line plus the reactive power delivered to the load. So this is again the feeder current squared multiplied by the reactance of the feeder plus Q of L. So this is 1.46 squared times 0.32 plus, we previously computed Q of L to be 4843 vars. So this will give us 4843.9 vars. So we now know the power and reactive power delivered by the source. That's two of the three unknowns we're being asked to compute. So the third unknown that we are left to determine is the voltage at the source side. Now we know that the apparent power delivered by the source, which is equal to V of source RMS multiplied by I of source RMS, will be equal to the square root of the power delivered by the source squared plus the reactive power delivered by the source squared. And if I compute that from the values of P of S and Q of S that I've already determined, I'm going to get 11111.8 volt amperes. Now, I of S, I can compute. I know the RMS value of I of F. I know the turns ratio of T1. I can compute for I of S. I of S is going to be N2 over N1 multiplied by I of F. By the way, no, this is N1, this is N2, and here this is N2, and this is N1. So what is this? This is 7967 over 230 multiplied by 1.46. And this will give me, actually, I of L, no? I of S ends up being the same as I of L, 50.51 amperes. Okay, thus, V of S is equal to S of S over I of S. So this is equal to 11111.8 divided by 50.51, which is now 220.03 volts. Okay. So my answers, P of S is this, Q of S is this, and V of S is this. In other words, okay, we expect a voltage drop across the feeder line, but to take into account that voltage drop, we only had to raise the intended load voltage by 0.03 volts. Let's compare examples 5 and 6. For examples 5 and 6, we have the same load that we want to supply. 10 kilowatts at 0.9 power factor lag. Meaning to say, the reactive power we want to supply to this load will also be the same. In example 5, the feeder current was 50.5 amperes. But in example 6, because of the step-up transformer coming from the source, the feeder current ends up being only 1.46 amperes. So because of that, from these values of power and reactive power lost in the transmission line, we were able to bring it down to these measly values. No? From 612.2 watts, we were able to bring it down to 0.51 watts. And from 816.3 vars, we were able to bring it down to 0.68 vars. So the requirements of the source in example 6 are much less than the requirements of the source in example 5. So this is what the source has to deliver in example 5, 10,612 watts, 5,659 vars, whereas in example 6, it only has to deliver 10,000.5 watts and 4843.9 vars. And to account for the voltage drop in example 5, the source voltage has to be raised to 238.1 volts to be able to supply 220 volts to the load. Whereas in example 6, we only had to raise it by 0.03 volts. Obviously, example 6 is a more economical setup than example 5. So inserting the transformers made the system much more economical to operate. And that's why our electrical distribution systems nowadays are AC. AC won over DC in the distribution of electric power when that was being decided toward the end of the 18th century. You have Thomas Edison, who was the chief proponent of DC, and you had Tesla, who was the chief proponent of AC. Unfortunately, or fortunately, AC won over DC. The reason is you can set up your distribution system to operate much more economically if you use AC. So this is your typical electrical power distribution system. We have power that is generated at a power plant. The voltage is stepped up and transmitted over high tension wire to wherever it's going to be needed, presumably someplace very far away. Then you're going to have a power substation to step up that very high voltage to an intermediate voltage. And then you're going to have a distribution substation that will transmit from that will bring down the voltage from that intermediate voltage to a still high voltage. And then finally, you're going to have your distribution transformers that are going to distribute to your houses, stepping down from that high voltage to your utility voltage. Your power substation at the high voltage side, you see voltages of up to 500,000 volts. The low voltage side would step down to that intermediate high voltage I was telling you about, which is about 115 kilovolts or 69 kilovolts. The distribution substation will step down from 69 kilovolts to 13.8 kilovolts. Okay? So this is already in your metropolitan area. You from the power substation steps it down before distribution to your metropolitan area. So in your metropolitan area, you might have a voltage, distribution voltage of 13.8 volts. These are the highest distribution lines that you see in your electric post, the very top of your electric post. And then your distribution transformer will step it down from 13.8 volts to 220 volts. So that's how electrical distribution works. For a residential area, you'll see this in the posts. For establishments, for large establishments, even enterprises, you're going to have a distribution transformer probably per building. Like I would imagine maybe outside of a triple E building, there will be a distribution transformer. Okay, let's take another example. Find V sub S and the power and reactive power supplied by the source. Assume the transformers are ideal. Okay. So we have a load. Okay. Here, this is a step down. Here, this is a step up. Okay, we didn't step up or step down too large in this particular example. We have 3 feeder lines. So Z3 is the likely represents the impedance of the feeder line that connects transformer T2 to the load. Z2 is the impedance of the feeder line that connects transformer T1 to T2. And finally, Z1 is the impedance of the feeder line that connects the source to T1. So let's solve this problem. Let's first try a phasor-based approach. I drew here the power triangle for the load. So the base of the triangle would be the power delivered to the load, which is 4,000 watts, 4 kilowatts. Okay. From the power triangle, I can compute for Q sub L. Q sub L is equal to P sub L, the tangent of the arc cosine of 0.9. And this is going to give me 1937.3 vars. Okay, let's make the voltage across our load our reference phasor. So let V sub L be our reference phasor. That is, the phasor V sub L is equal to 220 volts at an angle 0 degrees. Okay, from my complex power formula, so I'm taking a look now at the load. From my complex power formula, I know that the complex power at the load would be equal to my phasor voltage multiplied by the conjugate of my phasor load current. Okay. And I know this to be equal to P sub L plus J Q sub L. Thus, I can compute for the conjugate of my load current, that is equal to P sub L, which we know to be 4,000 watts, plus J Q sub L. Q sub L I have computed here, 1937.3 var, divided by V sub L, which is, this is 220 at an angle 0 degrees. And I'm going to get 20.20 at an angle 25.84 degrees amperes. Thus, IL is just going to be 20.20 at an angle minus 25.84 degrees amperes. Now let's take a look at the circuit again. I can compute for the value of E sub 4 using KVL. E sub 4 is equal to the voltage across Z sub 3 plus the voltage across my load. But the voltage across Z of 3 is equal to the phasor current I of L multiplied by Z of 3. So E of 4 is equal to I of L multiplied by Z of 3 plus the voltage across my load. So this is 20.20 at an angle minus 25.84 degrees multiplied by 0.3 plus J 0.4 plus 220 at an angle 0 degrees. And using our calculators, we come up with 229.02 at an angle 1.16 degrees volts. Okay. Is this reasonable? Well, remember the voltage across the load is 220 volts. We expect a voltage drop at Z3, so it's reasonable to expect E4 to be slightly larger than 220 volts. So this is how you audit your results, when you solve a problem. If you get a result that's less than 220 volts, then you know you must be doing something wrong. I can now compute for E3 and IX using the turns ratio of T sub 2. I can compute for the value of E3, the phasor E3, and the phasor IX using this turns ratio. E sub 3 is going to be equal to E sub 4 times 4 over 1. That's the turns ratio of transformer 2, which will give me 916.09 at an angle 1.16 degrees volts. And I of X is equal to I of L times 1 over 4. This is the inverse of the turns ratio, which is 5.05 at an angle minus 25.84 degrees amperes. So I now know E of 3 and I of X. I now know this voltage and I of X. I can now use KVL again to compute for E of 2. From KVL, E of 2 is equal to I of X Z of 2 plus E of 3. So this is now 5.05 at an angle minus 25.84 degrees multiplied by Z of 2 is 4.5 plus J6, 4.5 plus J6 plus E of 3, which we computed to be this, plus 916.09 at an angle 1.16 degrees. And again, using my calculator, I will get E of 2 is equal to 950.25 at an angle 2.16 degrees volts. Again, we should expect E of 2 to be slightly greater than E of 3, or maybe not slightly greater, but to be greater than E of 3 because of the voltage drop across Z of 2. And we did. E of 2 is 950.25, E of 3 is 916.09. finally, I can compute, well, not finally, no? But now I can compute for E1 and IS using the turns ratio of T1. I know Ix, I should be able to compute for Is of S. I know E2, I should be able to compute for Is of 1, knowing this turns ratio. Okay, E1 is equal to E2. The turns ratio for transformer 1 is 1:2. And I'm going to get 475.12 at an angle 2.16 degrees volts. And Is of S is equal to Is of X multiplied by the inverse turns ratio, 2:1, which will give me 10.10 at an angle minus 25.84 degrees amperes. I now know E1, I know IS. Again, using KVL, I will be able to determine V sub S. So from KVL, V sub S is equal to IS J1 plus E1. So this is 10.10 at an angle minus 25.84 degrees. J1 is 1.6 plus J 1.2, okay, plus this one, no? E1, 475.12 at an angle 2.16 degrees. And this is going to give me, okay, V sub S is equal to 495.10 at an angle 2.52 degrees volts. So this is the first quantity I'm being asked to compute. No? Let's go back to the problem. Find V sub S. In fact, we're only being asked for the RMS value of V sub S, not the phasor value. No? So V sub S, the RMS value of V sub S is 495.10 volts. Now, how do I determine P sub S and Q sub S? P sub S and Q sub S can be determined using the complex power formula. What is that? The complex power associated with the source will be the voltage, phasor voltage of my source multiplied by the conjugate of the phasor current through the source. Phasor voltage is 495.10. This is V sub S at an angle 2.52 degrees. And the conjugate of my phasor current is 10.10 at an angle, okay, you make the angle negative. It was originally negative, so it becomes positive, 25.84 degrees. Okay. If I compute this and display the results in rectangular form, I'm going to get 4400.47 plus J 2376.02. Now I know that this is equal now to the power supplied by the source, and this is now equal to the reactive power supplied by the source. So there are my answers. My voltage is 495.1, and these are my power and reactive power. Okay, is that the only way to solve the problem? No, there are many ways to solve this problem. I will offer an alternative solution. And this alternative solution involves successively referring quantities from the right side to the left side. So the first thing I'm going to do is I'm going to refer the load and J3 from the secondary of T2 to the primary of T2. Okay. So let J3 prime and VL prime be J3 and VL. Okay, this is a phasor referred to the primary of T2. Okay, J3 prime is equal to the turns ratio of T2, 4/1 squared, multiplied by J3. And I'm going to get 4.8 plus J, 6.4 ohms. What about VL prime? VL prime is equal to, okay, the turns ratio, okay, multiplied by V sub L. So this is V sub L multiplied by 4/1. And I'm going to get 880 at an angle 0 degrees volts. So what will my equivalent circuit look like now? My equivalent circuit will look as follows. No? I'll have my V sub S I have J1 so this is T1. These are my dot markings. What will I have here? I'm going to have J2 this was referred here to the secondary, so I'm going to get J3 prime and then my load was also referred to the secondary, so I'm going to get my load L, okay, where the load voltage now is VL prime. Okay. But this is still going to be 4 kilowatts at 0.9 PF lag. So it will still be the same power and power factor or power and reactive power. It's only the voltage that will change. Okay, what's going to be my strategy at this point? Okay, I can now refer all of these quantities to the primary of T1, to the primary of this transformer. So let J2 prime, J3 double prime, and VL double prime be J2, J3 prime, and VL prime referred to the primary of this time T1. Okay. So Z2 prime is going to be, okay, my T1 turns ratio, this is 1/2 squared multiplied by Z2, I'm going to get 1.125 plus J 1.5 ohms. Okay. Z3 double prime will be the same turns ratio squared multiplied by Z3 prime, which will give me 1.2 plus J 1.6 ohms. And finally, VL double prime will be VL prime multiplied by the turns ratio. So this is going to give me 440 at an angle 0 degrees volts. What will my equivalent circuit look like now? I will now have my source voltage V sub S. Z1 is as is. That has always been connected to the source. Okay. And then I will have Z2 prime. And then I will have Z3 double prime. Okay. And then I will have my load, okay, where now this voltage is VL double prime. And again, this will still be 4 kilowatts. This will still be 0.9 power factor lag. The only thing that will change is the voltage across it. Now recall, no? For the load, the complex power that is associated with the load is equal to VL double prime multiplied by the conjugate of your source current. No? So the complex power associated with this will be the voltage multiplied by the conjugate of this current. No? This is our source current. But we know this to be equal to the load power plus J times the load reactive power. And we've previously computed this in our first solution from the power triangle. From the power triangle, well, this is given 4,000, but we previously computed for Q of L, which is 1937.3 vars. So this is our PL plus J QL in volt amperes. So I can compute for Is of S prime, rather conjugate, which is S of L over VL double prime. So this is 4,000 plus J 1937.3 divided by 440 at an angle 0 degrees. I'm going to get 10.10 at an angle 25.84 degrees amperes. Or Is of S is 10.10 at an angle minus 25.84 degrees amperes. Note that in our first solution, this is exactly the same value we got for Is of S. My KVL now is going to be V of S is the total drop across these impedances plus V of L. No? So KVL, V of S is equal to ice of s multiplied by z1 plus z2 prime plus z3 double prime plus vis of L double prime. Okay, so if I just feed in these values in my calculator, so I know ice of s, I know z2 prime, I know z1, I know z2 prime, I know z3 prime, okay, and I know vis of L double prime, I'm going to get 495.10 at an angle 2.52 degrees volts. Again, this is identical to what we computed using the first approach. And the complex power will follow what we did in the first approach. S of S is equal to Vs multiplied by Is conjugate. Okay. This is going to give me 4,400.47 plus J 2376.02. And I know this to be P of S, and I also know this to be Q of S. So this is my V of S, this is my P of S, and this is my Q of S, which are consistent with what we earlier computed. Now here's a final alternative solution. So this is the third alternative solution. No, this is the second alternative solution which I'm showing. Okay. The first was successively using KVL, turns ratio and KVL. The second was referring everything from the right side to the left side. Now we're going to use power balancing. I claim this is the shortest solution, and the nice thing again about this solution is it does not require any complex math. No? Okay, so let's go back to the power triangle of the load. I can compute for S of L. This is PL over the power factor of the load. So this is 4,000 over 0.9. I'm going to get 4444.44 volt amperes. So this is 4444.44 VA. And from that, well, Q's of L, Q's of L we determined from here, no? No, sorry, yeah. Q's of L is this, 1937.3. We already determined that earlier. So this is 1937.3 vars. That's my power triangle. Now from this, I know that S of L is equal to, okay, V of L times I of L. Okay. So I can compute for I of L, which is S of L over V of L. I'm going to get 20.20 amperes. Okay, I now know the RMS value of I of L. I can get the RMS value of I of X. I of X is equal to I of L times the inverse turns ratio of T2, which is going to give me 5.05 amperes. So if I know the RMS value of I of X, I can get the RMS value of I of S, again using the inverse turns ratio of T1. So I now have is of s is equal to is of x multiplied by 1 over 2, and this will give me multiplied by 2 over 1, the inverse turns ratio, and that will give me 10.10 amperes. These three are important. What am I going to do? Okay. I can compute now for the power that is delivered by the source. Where will that power go? No? The power delivered by the source, part of it will be lost in R1, the resistive component of Z1. Part of that will be lost in R2, the resistive component of Z2. Part of that will be lost in R3, the resistive component of Z3. The rest of it will be delivered to the load. Okay. Nothing will be lost in T1 and T2 because that is how we defined in an ideal transformer. So P of S will be equal to P1, whatever is lost in the feeder 1, plus P2, whatever is lost in the feeder 2, plus P3, plus P of L. But what is P1? No? P1 is RMS value of I of S squared multiplied by 1.6. So I of S squared multiplied by R1. No? P2 is I of X squared multiplied by R2. And P3 is I of L squared multiplied by R3. Plus, finally you have P of L. Okay. So if I write this out, I don't think I really have to, but let me anyway. So this is 10.10 squared times 1.6 plus 5.05 squared times 4.5 plus 20.20 squared times 0.3 plus P of L, which is 4,000. I'm going to get 4400.47 watts. Okay. So that's one of the unknowns we were looking for, which is consistent with our previous answer. And we can do the same thing for Qs of S. No? Qs of S is equal to Q1 plus Q2 plus Q3 plus Qs of L. So this is IS squared X1, the reactive component of feeder 1, IX squared X2, this is, sorry, IX squared X2 plus IL squared X3 plus Qs of L. No? So this is IS squared. Okay, you have 10.10 times 1.6. Sorry, X1 is 1.2 plus 5.05 squared times 6 plus 10.10 squared times 0.4, 0.4 plus our Qs of L is 1937.3. And this will give me 2376.02 var. So this is another unknown we were asked to solve. Okay, that doesn't, we haven't determined yet what is the RMS value of P of S. What is the RMS value of V sub s? Okay, we know that the apparent power of the source, again this is not a phasor, is equal to the square root of Ps squared plus Qs squared, both of which we have already determined. No? This will give us 5000.96 volt amperes. But this is equal to V sub s times I sub s. Thus, V sub s is just S of s over I sub s. So this is 5000.96 divided by 10.10, and I'm going to get 495.1 volts. I'm going to get 495.1 volts. Okay. So those are my answers. Again, consistent. So the method does not require any complex math, but the method is only good for getting RMS values. It does not give us phasor values. What if I wanted to get the phasor value of V sub s? Well, I should be able to get the phasor value of V sub s. No? Note that we can compute for the angle between V sub s and I sub s. So I'm now talking about phasor values here through the power triangle. No? Because I know P sub s, I know Q sub s, so theta is the tangent of Q sub s over P sub s. Okay? And cosine theta is the power factor of my source. So if I know depending on which my reference is, anyway, I can get angles. No? I can get angles here. So knowing what my reference is, I should be able to get the angle of I sub s and V sub s if I wanted to. Let me cut this lecture here. I will finish the discussion of transformers in a part 3.